Fire Service Hydraulics Introduction. No exact allowances can be made for friction loss, since factors that influence it vary with condition, design manufacturer, age of the fire hose, and various appliances that may be attached. The NFPA handbook shows 5 different formulas for calculating friction loss. One of the formulas that greatly simplifies mental calculations on the fire ground without seriously affecting nozzle pressures is the Parrington formula, where FLR, or friction loss rate, equals 2Q squared. Q equals GPM divided by 100. Facts which you must have as a pump operator in order to determine pump pressure are: amount of hose in lay, diameter of hose, size of tips or GPM flowing, nozzle pressure, gravity loss and gravity gain, appliance loss and system loss. Formula to determine pump pressure. Depending upon the fire ground situation, there are several factors to consider for determining pump pressure. The following formula lists all of the possible considerations. Usually, at a minimum, you will solve for NP plus FLR. PP, or pump pressure, equals NP, or nozzle pressure, plus FLR, or the friction loss rate, times L, or length, plus AL, or appliance loss, then plus or minus gravity loss or gravity gain, plus SL, or system loss. Pump pressure. Pump pressure is the amount of pressure in pounds per square inch, or PSI, indicated on the pressure gauge or any given discharge gauge. This is the energy created by the pump which makes the water move through the plumbing on the fire engine. The pump pressure is telling you the amount of pressure being developed at the discharge side of the pump and up to the discharge outlets on the fire engine. The pressure registering on the pump pressure gauge will not be the same at the nozzle because energy or pressure is being used to overcome friction in the hose. Nozzle pressure. In determining pump pressure, the first part of the formula to be solved is nozzle pressure, or NP. This pressure, or PSI, is required because it is the pressure which is needed to make the tip of a solid stream or combination nozzle fog stream operate effectively. The common nozzle pressures include 100 psi for the automatic fog nozzles, 100 psi for a SelectoFlow fog nozzle, 100 psi for a master stream fog nozzles, and 80 psi for smoothbore tips for a master stream, 75 psi for a low pressure fog nozzle, and 50 psi for smoothbore tips that are on hand lines. Determining GPM flow. Let's look at an example for a hand line. To determine the GPM for an 1/8" smoothbore tip, we're going to use the formula GPM equals 30 diameter squared times the square root of the nozzle pressure. This formula is typically used on fire ground applications. The GPM in this case equals 30 times 1.125 squared times the square root of 50 for a hand line. GPM equals 30 times 1.27 times 7, and then this equals 266.7, or rounded off to 270 GPM for an 1 1/8" smoothbore tip. Let's look at a master stream appliance and determine the GPM for an 1 1/2" smoothbore tip. In this case, we will use the more precise formula for purposes of demonstration. GPM equals 29.7 times diameter square times the square root of the nozzle pressure. GPM equals 29.7 times 1.5 squared times the square root of 80 for a master stream. GPM equals 29.7 times 2.25 times 8.94, and this equals 597.4, or rounded off to 600 GPM. The following table has been provided to illustrate how we use this formula to determine the GPM flows for a variety of tips used in the fire service. Special note that an 1 1/4" tip can either be used as a hand line or a master stream. Friction loss rate, or FLR. The formula used to determine friction loss rate per length of 100 feet of hose is that FLR equals 2Q squared, and Q would equal GPM divided by 100. Let's look at an example. If you have 300 GPMs are flowing from a 2.5" hose with a fog nozzle, what is the FLR per 100 feet of hose? First, determine Q for quantity, which equals GPM divided by 100. Since 300 GPMs are flowing, Q equals 300 divided by 100, or simply 3. Next, place Q equals 3 into the formula FLR equals 2Q squared. FLR equals 2 times 3 squared, or 18. 18 psi equals the friction loss per 100 feet of 2.5" fire hose. Diameter of hose. The diameter of hose and GPM flowing determines the amount of friction loss for each 100-foot section. With a given flow, the smaller the diameter, the more friction loss involved. This is because a greater portion of the water pushed through actually comes into contact with the interior surface of the hose than in the case of the larger hose. A larger diameter hose allows a relatively larger percentage of the water pushed through to pass without contacting the interior surface. The formula for determining FLR is based on GPM through 2.5" hose. All flow rates through hose other than 2.5" must be converted to an equivalent 2.5" flow using conversion factors. To use these conversion factors, multiply the GPM times the factor to obtain the equivalent flow through a 2.5" hose line, and compute the friction loss based on this amount. Let's look at an example. If you have 150 GPM flowing through an 1 3/4" hose line, first you would take 150, multiply it by 2, which equals 300. Q would then equal 300 divided by 100, or simply 3. Length of hose. In order to solve the amount of friction loss in a hose lay, you must know the entire length of the hose lay. Friction loss factors are computed on 100-foot lengths of hose. When the length of the hose is unequal, as in a hose lay with a Siamese or gated Y, we generally use the higher friction loss rate and gate down the lower hose line at the gated Y. Use caution. Some organizations do not solve for the highest FLR. Instead, the friction loss rates are averaged. Know your organization's policy. Determining appliance loss. When water flows through small or large appliances, friction loss is produced. The loss will vary with the type of device, amount of water flowing, manufacturer age of the appliance, and organization's SOPs. In this presentation, we will consider the following for appliance loss. Small appliances, a gated Y appliance loss equals 5 psi. A Siamese appliance loss also equals 5 psi. Large appliances allow 15 psi for a deck gun attached to the engine, and also 15 psi for a ground monitor appliance. Use caution. How appliance loss is considered may vary from agency to agency. Know your agency's SOPs with regard to appliance loss. Determining gravity pressure. When hose lines are laid up or down an elevation, such as inclines, stairways, fire escapes, canyons, or the face of a tall building, the pressure loss or gain in pounds per square inch, which is exerted by the water, must be compensated for. It takes 0.434 psi to raise a column of water 1 foot, and for every foot below the level of the pump, you gain 0.434 psi. For fireground operations, the figure of 0.434 psi can be rounded off to 0.5 or half a psi per foot of elevation. So for a ladder pipe elevated 60 feet, you would compute 60 times half, which equals 30 psi. This 30 psi would be added to your pump pressure to overcome gravity loss. Standpipe and sprinkler systems.
System loss must be accounted for when pumping a fire department connection. When connecting to an FDC, 25 psi is factored when pumping a sprinkler or standpipe system. When determining gravity loss for a system, a rule of thumb for standpipe operations is to add 5 psi per story for 10 feet per floor, excluding the fire floor, since hose is actually laid on the bottom of the fire floor.
This means that a standpipe connection on the 3rd floor of a building would require 10 psi for gravity loss, again because hose is actually on the bottom of the 3rd floor. However, a sprinkler system on the 3rd floor would require 15 psi for gravity loss, since the sprinklers are on the ceiling of the 3rd floor.